The stellar-driven universe, a comprehensive theory of universal expansion, galactic formation, and temporal dynamics. Abstract. The stellar-driven universe theory introduces a revolutionary approach to cosmology, proposing that observable stellar phenomena can explain the universe's expansion and galactic formation. It suggests that the combined forces of solar winds and the remnants of population 3 stars are sufficient to account for cosmic expansion and galactic cohesion. Importantly, this theory is both a philosophical proposition and a scientifically rigorous framework that can be empirically tested. By grounding cosmological models in measurable forces, the stellar-driven universe presents a coherent and testable framework that combines scientific rigor with philosophical depth for understanding the cosmos. This emphasis on empirical testability underscores the scientific rigor of the theory and its potential for validation, stimulating intellectual engagement and curiosity and inviting further exploration and debate. Rethinking the universe. Current cosmological models, while widely accepted, struggle to explain several phenomena, including the universe's accelerating expansion and the gravitational behavior of galaxies. They heavily rely on the theoretical constructs of dark matter and energy to explain unobserved phenomena. Dark energy is postulated to drive the universe's accelerating expansion, while dark matter is thought to provide the missing mass required to explain the gravitational behavior of galaxies. However, these concepts lack direct observational evidence, leading to questions about their necessity. By proposing an alternative model rooted in observable phenomena, the stellar-driven universe theory aims to address these limitations and provide a more robust framework for understanding the cosmos. The stellar-driven universe theory challenges the necessity of dark matter and energy by proposing that the universe's large-scale dynamics can be explained through natural processes associated with stars, including solar winds, magnetic fields, stellar rotations, and gravitational effects from black holes. By focusing on forces that can be directly observed and measured, such as solar winds, magnetic fields, stellar rotation, and gravitational effects from black holes, this theory simplifies cosmological models. It offers a grounded alternative for explaining the structure and behavior of the cosmos. This grounded approach instills a sense of reassurance and confidence in its validity, providing a solid foundation for further exploration and discussion. The challenge of current cosmology. While widely accepted, the theories of dark matter and dark energy have emerged from observations that current models struggle to explain. Dark matter is believed to be responsible for the gravitational glue holding galaxies together, while dark energy is thought to counteract gravity, driving the universe's accelerated expansion. Despite extensive research and numerous experiments, these theoretical forces have yet to be directly detected, leading some to question whether they are necessary. The stellar-driven universe theory aims to address these cosmological challenges by proposing an alternative model rooted in observable phenomena, such as stellar activity, gravitational effects from black holes, and cosmic magnetic fields. This model posits that stellar activity, combined with gravitational effects from black holes and cosmic magnetic fields, provides a sufficient framework to explain cosmic expansion and galactic structure. Universal expansion via solar winds. A new perspective on expansion. What if the outward pressure of solar winds mirrors processes we see in biological systems, like cellular division or growth? This analogy might inspire further exploration into parallels between cosmological and biological phenomena. The concept of solar winds as an expansive force. Stars continuously emit charged particles known as solar winds. The force of these emissions may seem negligible on a local scale. However, The cumulative effect generates an outward pressure that could drive universal expansion across countless stars in billions of galaxies. Rather than relying on dark energy, this theory suggests that the combined force of stellar solar winds could push galaxies apart, producing the observed acceleration in the universe's expansion. Types and intensities of solar winds. Different types of stars emit solar winds at varying intensities, with massive stars like supergiants producing stronger winds. This variability can contribute to regional differences in cosmic expansion, as areas with denser populations of massive stars might experience more significant outward pressure. Impact of stellar life cycles on expansion rates. As stars evolve and eventually die, they release vast amounts of energy through supernova explosions. These events contribute significant outward pressure, further fueling cosmic expansion. This dynamic change in stellar wind output across different life stages of stars might explain the varying rates of expansion observed over cosmic time. Cosmic magnetic fields as an expansive force. The role of cosmic magnetism in expansion. Solar winds are accompanied by magnetic fields that interact with the magnetic fields of other stars and interstellar space, potentially enhancing their influence on galactic dynamics. Unlike traditional theories that focus on static or localized effects, this interaction emphasizes the large-scale, cumulative impact of magnetic fields in driving cosmic expansion. This magnetic interaction enhances the repulsive force between galaxies, providing a natural mechanism for accelerated expansion. Cosmic magnetic fields act as a multiplier, amplifying the effect of solar winds and contributing to the large-scale expansion of the universe. Observational evidence of cosmic magnetism. Galactic clusters often exhibit detectable magnetic fields, which could align with the stellar-driven universe's predictions. By acting as a medium that strengthens the effect of stellar winds, cosmic magnetism provides an observable mechanism for universal expansion, supporting this theory over dark energy models. Population 3. Stars as the seeds of galactic formation. Formation of primordial black holes. Population 3 stars, the first generation, were massive and short-lived. Upon reaching the end of their lives, these stars went supernova, leaving behind black holes that became gravitational anchors for future galaxies. In this theory, these black holes serve as the seeds for galaxies, gathering surrounding gas and matter and creating galactic centers. Black hole seeds without dark matter. In traditional models, dark matter is hypothesized to stabilize galaxies. However, the stellar-driven universe suggests that these supermassive black holes can anchor galaxies, making dark matter unnecessary for explaining galactic cohesion. This natural gravitational center, created by population 3 black holes, offers a grounded explanation for galaxy formation and stability. Implications for galactic cohesion. Galactic cohesion is achieved through the gravitational pull of these black holes, complemented by observable matter within galaxies. This approach resolves challenges posed by dark matter-dependent models by attributing stability and cohesion to measurable gravitational interactions rather than unseen forces. Galactic shape, determined by primordial star rotation. Rotational dynamics of population 3 stars. The rotational speed of population 3 stars during their collapse likely influenced the shape of their resulting galaxies. Faster rotation leads to more incredible angular momentum, which can result in a disk-like structure typical of spiral galaxies. Slower rotation produces more isotropic distributions, forming elliptical galaxies, predicting galactic morphology based on stellar rotation. This theory proposes that galactic shapes, such as spiral, elliptical, and irregular, are determined by the rotational properties of population 3 stars. Observing correlations between the rotation rates of modern galaxies and their shapes could validate this model, providing an alternative to dark matter explanations for galactic morphology. Tools such as advanced spectrographs and simulations of angular momentum distribution would be essential in establishing these correlations. Time as an emergent phenomenon linked to motion. Time perception relative to motion. Traditionally, time is regarded as an unchanging dimension that flows uniformly, unaffected by an object's motion or position in the universe. This theory, however, proposes that time is experienced differently based on relative motion, which refers to an object's velocity and position relative to the universe's overall framework of movement and expansion. An object at zero velocity relative to the universe may perceive time instantaneously or not at all, suggesting that time is not an absolute constant, but an emergent property influenced by movement. Quantum implications of zero velocity. Achieving zero velocity relative to the universe could lead to unique quantum behaviors, potentially collapsing uncertainties in time perception. This theory suggests a link between quantum mechanics and time as an emergent phenomenon tied to cosmic motion. Experimental and observational proposals. Testing this idea could involve studying time dilation effects near black holes or attempting to measure time at different states of cosmic motion. Observing these effects could provide valuable insights into the nature of time and its relationship with motion, supporting the stellar-driven universe's alternative view of temporality. Observational tests and future predictions. A call to interdisciplinary exploration. Beyond traditional astronomy, could fields like quantum mechanics and systems biology offer new tools to validate this theory? Interdisciplinary approaches might unlock unique insights into the interconnected forces driving cosmic behavior. Galactic motion data as evidence. This theory can be tested by analyzing galactic separation rates relative to stellar density using datasets from observatories like the Hubble Space Telescope and the James Webb Space Telescope. Observations showing that galaxies with denser star populations exhibit accelerated expansion would support the stellar-driven universe model. Local galaxy comparisons. Observing interactions within the local group, including galaxies like Andromeda and the Milky Way, could reveal patterns consistent with solar wind-driven expansion. By studying localized interactions, we might gain further insights into the forces influencing galactic separation. Addressing counter-arguments and challenges. Solar wind accumulation over cosmic distances. Some may question whether solar winds are strong enough to drive separation across vast distances. However, the cumulative effect of these forces, akin to small tidal forces generating substantial ocean movements, may influence galaxies' expansion over cosmic scales. The role of black hole anchors in galaxy formation. While critics may question if black holes alone can account for galaxy formation, this theory emphasizes the role of angular momentum and accretion dynamics in creating stable, diverse galactic structures without requiring dark matter. Philosophical implications of the stellar-driven universe. Posing the big questions. Does understanding the universe as a living system redefine humanity's role within it? Could this perspective influence how we approach cosmic exploration and our responsibility as participants in this dynamic system? These questions invite deeper reflection on our connection to the universe and the forces that shape it. Cosmic connection to human perception of time and movement. If time is indeed a dynamic property tied to motion, it challenges our fundamental understanding of reality. How might civilizations in different regions of the universe, experiencing varied cosmic velocities, perceive the flow of time? Could this lead to vastly different technological or philosophical developments across the cosmos? The universe as a living system. This perspective likens the universe to a vast, self-organizing organism where stars, galaxies, and cosmic forces are its organs working in concert. What lessons can humanity draw from this interconnectedness to apply to its own systems and societies? Viewing the universe as alive bridges science and philosophy, opening doors to explore cosmic purpose and evolution. Conclusion: a new paradigm in cosmology. The stellar-driven universe offers a grounded alternative to dark matter and dark energy models by focusing on tangible, measurable forces like solar winds, magnetic fields, and stellar dynamics. This theory challenges traditional cosmology and redefines time as an emergent relative experience influenced by cosmic motion. It opens new avenues for scientific research, philosophical inquiry, and understanding of our place in the cosmos. With this model, we are invited to explore the universe not as a static system, but as a dynamic, evolving entity driven by forces we can observe and understand.